Hey, welcome to the G Lab. This is Mr. G. Today, atomic structure, how to draw cool-looking and accurate atoms. You will be a master of looking at the periodic table and being able to draw an atom from any element on that table. Wow. Well, at least the small ones. This is the periodic table. Ta-da! Today we're going to start off with carbon, letter C on the periodic table. Now let's talk a little quick about letters in the periodic table. If you see that each one of these here has a name and a symbol, if you happen to notice the letter C somewhere, that simply means that you have an atom of carbon. It's an element. An element on the periodic table, an element is simply one of these individual boxes, and it is a unique type of atom that that is different from all the other types of atoms that are on here. It's the most basic form of matter in a sense. Now if you see CO, you might go, oh, let's look around and see if we can find a CO. And hey, there it is. Number 27 here is cobalt. That's an element on the periodic table called cobalt. It's an element. If you see, for instance, why didn't they call carbon Ca? Well, the problem was that Ca was already taken. You got calcium down there, you got cobalt. So some of them just have one big letter, some of them have two letters, one big and one small. And what if you see, for instance, this, CO, with C capitalized and O capitalized? Well, if you look around, there's none of these that actually have one big letter and one small letter. They're all uppercase then lowercase, or just one letter. So what this means here, C and an O, is that these are actually two separate elements, and they are bonded together. This is a compound called carbon monoxide. It's a carbon stuck to an oxygen atom, two separate atoms. So keep an eye on which letters are capitalized and which aren't, and that will help you determine which one's which. All right, now some of these don't make any sense at all, like iron, for instance. Why didn't they just use I? Well, iodine is I. Why didn't they use IR? They could use IR for iron, right? Well, actually, no. IR actually stands for iridium, right here, number 77. How about IN? Oh, that's taken. So some of these they decided we're going to use the original Latin word. And in this case, it's ferrum, means iron, kind of like a Ferris wheel is a big iron wheel. And so Fe is the first part of the Latin word ferrum for iron. Here's gold. Gold is aurum, is the Latin word for gold, and that's why they used Au. Similar thing with many of these other ones like silver, for instance, or tungsten, or many of the other ones that don't really quite make sense. Some of the ones down here are named after famous people in the discovery of the atom. So Rutherford here is honored here, and here's borium, named after Niels Bohr, and so forth. Okay, back to carbon. Here is what carbon looks like. This is my best representation of a carbon atom. There's a nucleus in the center, and whirling around the outside is the electron cloud. The electrons are moving so fast that essentially it is just a cloud, a region of space where you're not exactly sure where those things are. But what we tend to do when we draw atoms is to pretend like we can freeze that in place, and we draw them showing their exact orbits. Now, how do you know how many protons, neutrons, and electrons to draw? That is the subject of today's talk. So here we go. Atomic number is the key number here, number 6. And 6 tells you one main thing. It's the number of protons in the atom. So the positive charged particles in the center and the nucleus here are protons. This number right there is the number of protons. If it had more protons, if it had 7, for instance, that would be the next number on the periodic table, which is 7, which is nitrogen. It would be a whole different kind of element. So 6 is the number of protons. It's the atomic number. And what do we know about protons? They have a positive charge, and they're found in the nucleus. Now, electrons are found out here orbiting around the outside. They have a negative charge. So how many electrons do you need to draw? How many electrons are included in a carbon atom? Well, it's pretty easy to figure that out. Generally, we're going to be drawing neutral atoms. In other words, they have no charge. So if you have 6 positives, how do you make that neutralize? How do you neutralize that? How do you make it just simple neutral with no charge? Well, you've got to have 6 minuses. That's 6 electrons. So if 6 protons, 6 electrons, they essentially will cancel each other out and make the overall net charge of the atom neutral. So 6 protons, 6 electrons. The atomic number tells you the number of protons. It also is going to be the number of electrons in a neutral atom. Pretty simple. Simple so far, right? Now, the other thing we've got to consider is how many neutrons do we have? Well, neutrons have mass, protons have mass, neutrons have no charge. They are neutral atoms. So they don't affect the neutrality of the atom. They're already neutral. So what do we know about mass, though? Protons have a mass of 1. What we call an AMU, atomic mass unit, which is obviously a very small measure of mass. So protons have a mass of 1, and neutrons also have a mass of 1. They weigh essentially the same amount. So how do we know how many neutrons to put in there? We need to look at how much this nucleus weighs. What's the mass of the nucleus so far? Well, if we count all these up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, we have 12 atomic mass units. The mass is 12. Huh. Does that look like anything familiar? Oh yeah, look at that, the atomic mass over here, 12. Number of protons plus the number of neutrons. Essentially, it's just the mass of the nucleus. All right, now the question, of course, many people ask is, well, what's the deal with this 0.01? This is not exactly 12. If these all weigh exactly 1, why is that not exactly 12? Is it the electrons? Do they have some sort of mass? Well, electrons do have a little bit of mass, but look at the scale here, 0.000000. This would keep going for quite a while, and somewhere way out here would be a 1. Now, if you have 6 of those, is that enough to add up to 0.01? No, it's not. And if you look on the periodic table, there are other places where you have elements that have something 0.99 or something 0.97 or something 0.24. And so these aren't always right above there, and so these are not the electrons that are giving it that extra mass. What's going on here? Where is that 0.01 coming from? Well, here's where it's coming from. If you go out in nature and look for carbon atoms, you will find carbon atoms, they all have 6 protons. They have to have 6 protons, otherwise they wouldn't be carbon. But if you look at the mass of these, 12 is their mass. It doesn't match up. If you look very carefully at these naturally occurring carbon atoms, you will find 1 out of every 100 carbon atoms that has 1, 2, 3, 4, 5, 6, 7, what? 7 neutrons and 6 protons. That's a mass of 13. So 1 out of these 100 is what's called an isotope. It's an atom with an unusual number of neutrons. So an isotope is simply an atom with an unusual number of neutrons. In this case, it has 1 extra neutron compared to your average normal carbon atom. So its mass is 13, and we call that carbon-13. It has that mass. About 1% of all carbon atoms are carbon-13, and 99% of carbon atoms are carbon-12. So if you were to average the mass of all of these atoms, you would find that 12 plus 12 plus 12 plus 12 plus 12, 12, 12, 12, 12, 12 all the way up here till one of them is 13. That's going to bring your average mass up just a little bit. It would come up with a mass of 12.01. Now, if this was carbon-11, if it had 1 less neutron, for instance, than the average carbon atom, that would drag your average atomic mass down a little bit. It would be 11.99. So it kind of depends on what you find out there in nature. Some isotopes are a little bit heavier, some isotopes are a little bit lighter, and isotopes in general are radioactive. They're trying to become more stable, and so they may get rid of some of these extra particles. And when those particles come flying off, that's what radioactivity is. And can obviously do some damage to your cells, for instance, and cause cells to reproduce uncontrollably, causing a tumor. And that's what we call cancer. Okay, so that's the deal with the atomic mass. Back to our story here. What do we have? In this case, carbon has 6 protons, 6 neutrons, 6 electrons. No problem. Simple. All right, let's try another one. Oxygen. Take a look at this one. Can you figure out the number of protons, neutrons, and electrons? If you want to try it on your own, pause the video. If not, here we go. Atomic number tells you the number of protons. So you've got 8 protons, obviously, right there. Boom, we can draw those in the center. What about neutrons? How do we find the number of neutrons? Well, we got to look at the atomic mass. Atomic mass is 15.999. That's almost 16, so we're going to round that off to 16. Your normal oxygen atom has 16 atomic mass units. That's its mass. So what do we know so far? Atomic mass is the number of protons plus the number of neutrons. Well, let's find the mass. What do we have so far? We only have 8, but we need to have 16 for atomic mass. So 8 plus something, 8 protons plus some number of neutrons should get us 16. Fill in the blank. Pretty easy. That's easy. 8 neutrons will give us a total mass then of 16. And that is your normal oxygen atom. 1 out of every 1,000 oxygen atoms might have a mass of 15, but we're going to stick with the normal ones. 16 is your total mass. Awesome. All right, now electrons. What do we do for electrons? Well, we're going to go with, this is a neutral atom. We're just going to assume that it's neutral unless we are told otherwise. And we have 8 positives, so we need to balance that out with 8 negatives. And those will create a neutral atom. 8 negatives means we've got 8 electrons. So we put 2 in the first shell. The first electron orbit here can hold up to 2, and then it's full. So the other 6 electrons, we've already used 2. The other 6 have to go in the next orbital shell out. So we'll put 6 more out there for a total of 8 electrons. No problem. So boom, 8 protons, 8 neutrons, 8 electrons. This is easy. Is it always the same? 6, 6, and 6, or 8, 8, and 8? Is it going to be, 4, 4, and 4, for instance? If we try, say, this element, beryllium, atomic number is 4. Go ahead and try and draw this one. Pause the video if you want to draw it. All right, welcome back from pausing. And let's take a look. Atomic number is 4, so you've got 4 protons. All right, that makes sense. Atomic mass. Well, let's see here. Atomic mass is 9. So we've got 4. If we have the mass of the nucleus here altogether, we only have 4. We need to get up to 9. What do we need to add? Well, 4 plus something equals 9. That's right. It's 5. All right, so in this case, we have a different number of neutrons than we do protons, and that's okay. Some atoms are just like that. They're just found more often like that. So this one here, your usual beryllium atom is going to have 5 neutrons. And then what about electrons? Again, here we go, neutral atom. This one has 4 protons, therefore it's got to have 4 electrons to make it neutral, to balance it out. So 2 in the first shell and 2 in the next shell. And there you have it. There is beryllium. 4, 5, and 4. Not always the same number here, so be careful. You've got to do a little bit of math to find the number of neutrons. Sometimes it's the same, sometimes it's not. All right, let's take a look real quick at aluminum. This is a bigger atom, obviously. Look at the size of this thing. 13 protons in the center. Atomic mass, let's figure out how many neutrons. Atomic mass is about 27. We round it off to 27. So what does that tell us? We need to have 13 plus something. Oops, went too fast. 13 plus something gives us a mass of 27. How many neutrons do we need to add in here? That's right, 14. 14, add those in there, and you're going to end up with atomic mass of 27. Perfect. The number of electrons, pretty simple, right? Always the same as the atomic number up here to keep a neutral atom. So we've got 13 electrons. 2 of them are in the first shell. And then we can fit 8 of them in the next shell. That's the maximum. That only gets us 2, 3, 4, 5, 6, 7, 8, 9, 10. But we have 13 electrons. Where are we going to put the next 3? Well, we've got to have another shell, the third orbital shell, and we'll put the other 3 out there. It can hold them no problem. All right, so there is a maximum number of electrons per orbital shell. 2 in the first, that's the maximum, and then it's full. It can't hold any more. In the next shell, it's 8, and then it can't hold any more. So if you still have more electrons, you've got to put them in the next shell. This next one can hold 8 as well. You can have a 4th shell. You can have a 5th shell and a 6th shell. They get a little more complicated with subshells and suborbitals. And the next shell can hold 18, and the next one, and so forth. But we're going to stick with the smaller atoms. And so 2, 8, and 8 are the numbers you need to remember for those first 3 shells in terms of what they can hold. So what do we have? Do we have a normal 13, 13, 13? Nope. This one here is a 13, 14, 13. All right, hopefully this gives you enough tools to be able to draw any of the atoms, at least in the first few rows of the periodic table. You are now becoming a master of atoms, of the periodic table, and this will give you the basis for how chemistry itself works.